Hi guys, so in this video tutorial, I'm going to teach you how to convert decimal number system to other bases such as base 2, base 8, and base 16. So given a number in decimal, I'm going to teach you how to convert it to base 2, base 8, and base 16. Okay, so say for example, we are given the decimal number 42. So how do we convert this to other bases in base 2, base 8, and base 16? So let's start first converting it to binary. So to convert decimal to binary, we simply divide the decimal number by 2. So we have 42 divided by 2. 42 divided by 2 is 21. So 2 times 21 is 42, therefore there is no remainder. Again, we divide 21 by 2. That is 10. Then we multiply 2 by 10, that is 20. So it means to say there is a remainder 1. So we continue dividing the number until we reach 1. So again, we have 10 divided by 2. This is 5. We have 2 times 5 is 10, so no remainder. We proceed to 5 divided by 2, that is 2. 2 times 2 is 4. So therefore there is a remainder 1. Then 2 divided by 2 is 1. No remainder, so we put there 0. So we rewrite the number following the least significant digit up to the most significant digit. Okay, so we arrange it upwards. So we have 1, 0, 1, 0, 1, 0. So this is now the binary equivalent of 42. Now, to convert this to octal, we simply rewrite the number 1, 0, 1, 0, 1, 0. And then we group the number by 3. Since we know that in octal is represented by 3 binary digits. Okay? So, starting from the right, we group the numbers, the binary digits into 3. So we have here 1, 2, 3 group, and then 1, 2, 3. Now, to convert this to octal, we follow again the positional value, which is 1, 2, 4, and then 1, 2, 4. Right, then we only add the number, we only get the number which is opposite 1. So in this group we have 2, and then in this group we have 1 and 4, so we add 1 plus 4, that is 5. So therefore 42 in octal is 52. Then we proceed with the last number system, which is hexadecimal. So to convert again that number to hexadecimal, we use the binary digits or the equivalent binary digit 1010. This time, since this is hexadecimal, we're going to group the number by 4, starting at the right. So we have 1, 2, 3, 4 there. Okay, so why 4? So we group this by 4 because we know that each hexadecimal digit is equivalent to 4 binary digits. So again, using the positional value 1, 2, 4, this time we have 8 because we have 4 digits, and then we have 1 and 2. Again, we follow the same procedure. For each group, we add the numbers which is opposite 1. So in here we have 2 plus 8. So 2 plus 8 here is 10. But we know that in hexadecimal, 10 is represented by the letter A. And then we have here 2. So we have 2A as the hexadecimal equivalent. Okay, let's have another example of conversion of decimal number to base 2, to base 8, and to base 16. Say for example, you are given the decimal number 125. So how do we convert this to other bases? Again, we divide this by 2. So dividing 125 by 2, we have 62. Then we multiply 2 by 62, we have 124. So we have a remainder of 1. So we continue dividing it by 2. We have 31. So this is 0. 31 divided by 2 is 15. So we have the remainder of 1. And then 15 divided by 2, we have 7. So we have a remainder of 1. Divided by 2, we have 3. So we have a remainder of 1. 10 divided by 2, we have 1. So we have a remainder of 1. Then we're going to write this upward. So we have 1, 1, 1, 1, 1, 0, 1. So this is now the binary equivalent. So again, to convert it to octal, we are going to use the binary digits. So we have to rewrite it 1, 1, 1, 1, 1, 0, 1, and then we are going to group this into 3, starting from the right. So we have 1, 0, 1, that is one group, and then 1, 1, 1, that is one group. Okay, so following again the positional value, we have 1, 2, 4, and then 1, 2, 4, and then 1. We add the values which is opposite 1. So we have 1 plus 4 here, we have 5. We have full 1, 1, 2, 4, we have 7. And then we have 1, that is 175. So the octal equivalent is 175. To get the hexadecimal, again, we're going to use the binary equivalent 1, 1, 1, 1, 1, 0, 1. This time, we are going to group the numbers into 4, starting from the right. So we count 1, 2, 3, 4, group. Again, we use the positional value 1, 2, 4, 8. Then we have 1, 2, 4. So we add only the values which is opposite 1. So we have 1 plus 4 plus 8. So 8 plus 4 here is 12 plus 1, 13. But we don't use 13 in hexadecimal. So we write D because that is the equivalent of 13. And then we have full ones here. We have 1, 2 plus 4, we have 7. So the answer is 7D. That is the hexadecimal equivalent. So we are still on the conversion of decimal numbers to other bases. So let's have our last example. Say you are given 210 in decimal. So how are we going to convert this to other bases? So that we could easily get the octal and the hexadecimal equivalent, we are going to convert this first to binary. So to do that, we divide it by 2. So 210 divided by 2, we have 105. Then we multiply it. If there is no carry, we put here 0. 205 divided by 2, we have 52. So if 2 multiplied by 52, we have 104. So we have a remainder of 1. Again, divided by 2, we get 26. That is 0 remainder. Grouped by 2, divided by 2, we have 13. Again, 0 remainder. Divided by 2, we have 6. That is remainder 1. Divided by 2, we have 3. Remainder 0, and then we divided by 2, we have 1, remainder 1. So we are going to write this upward here. So we have 1, 1, 0, 1, 0, 0, 1, 0. So this is now the binary equivalent. Now out from the binary equivalent, we can easily get the octal and hexadecimal equivalent. So we simply rewrite 1, 1, 0, 1, 0, 0, 1, 0, and then we group this into 3 to convert it to octal, starting from the right. And then we use the positional value. So this is 1, 2. So this is 2, this is 2, and this is 3. So the octal equivalent is 3, 2, 2. Okay, convert it again to hexadecimal. We simply rewrite the numbers, and then this time we group it into 4. So we have 2, 3, 4, 1, 2, 3, 4. And then using the positional value, we have 1 and 2, 2. This is 1, 2, 4, 8. So 4 plus 8 is 12 plus 1 is 13. So 13 is D in hexadecimal. So the hexadecimal equivalent is D2.